Esters are sweet-smelling, naturally occurring organic compounds that contribute to fragrances and flavors of flowers and fruits. For example, ethyl methanoate smells like rum and contributes to the flavor of lemon and strawberry food products. Esters have relatively low boiling points when compared with alcohols and carboxylic acids of similar relative molecular mass and are generally immiscible with water. Long carbon chain esters are commonly found in vegetable oils and animal fats and are generally used in food preparation and soap making. Esters are formed from the condensation reaction of organic acids and alcohol under acidic conditions. A condensation reaction is one where a large molecule is formed from smaller molecules with the elimination of a small molecule such as water. The process by which an ester is formed is known as esterification and can be carried out in the laboratory by heating an excess of an organic acid with an alcohol in the presence of strong mineral acid such as concentrated sulfuric acid under reflux. The mixture is heated in a round bottom flask which is attached to a condenser which condenses the alcohol vapors from the heated mixture which then drips back into the reaction mixture, ensuring that the reaction continues to completion. The resulting mixture is then fractionally distilled to obtain the ester. When an organic acid reacts with an alcohol, water is eliminated. The water is formed from the hydroxyl group of the organic acid and the hydrogen atom from the hydroxyl group of the alcohol. The ester is then formed from the residues of the acid and alcohol. When naming esters, the alkyl group name of the alcohol is written first, followed by the stem name of the organic acid, to which anoate is added, resulting in the salt name of the acid. For example, ethyl from ethanol and propanoate from propanoic acid result in the ester ethyl propanoate as shown in the equation above. Some examples of esters and the alcohols and acids from which they are formed are ethanoic acid, hexanol, hexyl ethanoate, propanoic acid, pentanol, pentyl propanoate, butanoic acid, propanol, propyl butanoate, pentanoic acid, ethanol, ethyl pentanoate, hexanoic acid, butanol, butyl hexanoate. Hydrolysis is a splitting of a large molecule into smaller molecules by the addition of water. Hydrolysis is the reverse of condensation. When water is added to an ester under alkaline or acidic conditions, the ester splits to produce the alcohol and the organic acid from which the ester was made. Hydrolysis under alkaline conditions results in the acid produced reacting with the alkali to form the salt of the acid. In the first equation, acidic hydrolysis, an acid and an alcohol are formed. But in the second equation, alkalinic hydrolysis, a salt of the acid, sodium propanoate, is formed and alcohol. Saponification is the process by which soap is made. Generally, saponification is the alkaline hydrolysis of long-chain esters in fats and oils to form glycerol and the salts of the fatty acids, carboxylic acids. Fats and oils are formed from the reaction between propane 1,2,3-triol, a trialcohol known as glycerol, and naturally occurring long-chain organic acids called fatty acids. A single molecule of glycerol combines with 3 molecules of fatty acids by way of ester bonds to form a triglyceride. The alkaline hydrolysis of fats and oils produces glycerol and the salts of the fatty acids. The alkalis used are chiefly potassium and sodium hydroxides, hence Soaps are sodium and potassium salts of fatty acids. Soapless detergents are generally the sodium and potassium salts of alkyl benzene sulfonic acid, a petroleum derivative. For example, sodium dudecyl benzene sulfonate is the active ingredient in many laundry detergents. The structure shows a sodium salt of an alkyl benzene sulfonate. The term detergent is generally used for any form of cleaning agent with lathering effects. Detergents are used in the removal of dirt or other foreign matter from contaminated surfaces. A common feature of detergents is that they are made up of relatively large molecules. One part of the molecule is soluble in organic substances and the other part is soluble in water. Detergents may be soapy or soapless, synthetic. Using only water is not good for cleaning because water has poor wetting properties and a high surface tension. Surface tension is the ability of the molecules below the surface of a liquid to exert an inward pull on the surface molecules of the liquid. It is this property of water which causes some substances to float around in water before they are dissolved or become wet immediately. Water and grease are immiscible because water is a polar substance while grease is not. When detergents are placed in water, the force that pulls the molecules of the water together is reduced, causing less tension on the surface of the water. When this happens, grease and dirt molecules are more able to spread throughout the body of the water. Detergents have two main parts, the head and the tail. The head. This part has polar characteristics and tends to attach itself to water. It is water-loving or hydrophilic. The tail. This part has nonpolar characteristics and tends to attach itself to dirt and grease. It's grease-loving or hydrophobic. The X in the formula represents any number of combination of CH2 in the formula that makes up the tail of the detergent. The tail of the detergent is a hydrocarbon combination which is nonpolar and unable to attach to water. It's hydrophobic, but it's able to attach to grease and dirt. The head is slightly positive and negative at different atoms in the molecule. It's polar and is able to attach to water, hydrophilic, but not to grease and dirt. The tails of the detergent, which are grease-loving, move towards grease or dirt on fabric. They attach to the grease and form an emulsion. This emulsion is now able to be washed from the fabric due to the head of the detergent being water-loving. Grease and dirt are lifted from the fabric and carried away as an emulsion by the detergent. Soapy detergents are made from hydrolysis of fats and oils. They are biodegradable. They cause scum formation with hard water as the calcium and magnesium ions present in hard water form insoluble salts with soap molecules and precipitate out of the solution. They lather well with soft water. They are widely used for domestic purposes but can alter fabric color over long use. Soapy structures are normally sodium or potassium salt of a long-chain carboxylic acid. Soapless detergents are made from petroleum derivatives. Most are non-biodegradable. They do not cause scum with hard water as the calcium and magnesium salts of sulfonic acids are soluble in water. They have effective cleaning power in both soft and hard water. They are widely used in industry for cleaning, softening of leather, and suppressing dust. Soapless structures do not have the COOH carboxyl group. Instead, they consist of either sulfate or sulfonate groups. A large number of naturally occurring substances are polymers, including cellulose, rubber, cotton, starch, proteins, and nucleic acids. Mankind has become so heavily dependent on polymers that about 80% of the world's output of organic chemicals is used to make synthetic polymers. Synthetic polymers include substances such as polyvinyl chloride, PVCs, polyethylene, perspex, terylene, Teflon, rayon, styrofoam, silicone plastics, and nylon, all of which are a routine part of our daily existence. Polymers vary a great deal in their physical properties and therefore the use to which they are put. Generally, those that are very strong and not easily stretched are used as fibers, and those that are usually carbon-based and can be shaped by applying heat and/or pressure are classified as plastics. Polymers are substances that consist of very large molecules called macromolecules, which are made up of many repeating molecular structural subunits typically connected by covalent bonds. Monomers are considered to be the building blocks of polymers. In other words, they are the molecular subunits used to synthesize the polymers by way of reactions called polymerizations. It is useful to note that not all macromolecules are polymers. However, all polymers are macromolecules and can have 10,000 or more monomer residues in a single chain. An essential concept which defines polymer structure is repeating unit. This is the simplest structural unit of a polymer chain, so a polymer essentially consists of repeat units linked together by covalent bonds. Polymers can be classified based on the type of reaction, addition or condensation that occurs between the monomers or the type of bond or link that exists between structural subunits, monomer residues of the polymers. Polymers can also be simply classified as either natural or synthetic. Addition polymers are synthesized by addition reactions occurring between the molecules of the monomer. An unsaturated monomer, that is, one with a double bond between two carbon atoms, adds on to a growing polymer chain one at a time. In this type of polymerization, a single monomer gives rise to a single polymer with no other reaction products. Addition polymerization results from alkene-like monomers reacting. Hence, these polymers are often termed polyalkenes. Condensation polymers are synthesized by condensation reactions occurring between the monomers. In this type of polymerization, the bonding between two monomers is characterized by the loss of a small molecule, usually water. The monomers for condensation polymerization have two main characteristics. Firstly, they possess functional groups such as hydroxyl, amine, and carboxylic acids, and secondly, each monomer has at least two reactive sites, which usually means two functional groups. The reaction of these functional groups results in the polymer being built up and the corresponding elimination of a small molecule. If the bond between the monomer residues is an amide bond, the polymer is classified as a polyamide. If the ester link is formed, the polymer is classified as polyester, and in a polysaccharide, the monomer residues are linked by glycosidic bonds. During the polymerization of ethene, thousands of ethene molecules join together to make polyethene. The number of molecules joining up to form a single chain, N, is very variable, but is in the region of 2,000 to 20,000. Reaction conditions can be varied to produce high density and low density polyethene, HDPE and LDPE respectively. Low density polyethene has quite a lot of branching along the hydrocarbon chains, and this prevents the chains from lying uniformly close to each other, hence resulting in a relatively low mass per unit volume of polymer. Low density polyethene is primarily used to make low strength plastic items such as plastic bags and bottles, corrosion resistant work surfaces, food storage containers, etc. High density polyethene has very little branching along the hydrocarbon chains, hence they lie uniformly close to each other, resulting in its density being higher because of the better packing and smaller amount of wasted space in the structure. High density polyethene is used to make things like milk and juice bottles, kitchenware, fuel tanks, fences, plastic pipes, and buckets, etc. Polychloroethene, also called polyvinyl chloride or PVC. Polychloroethene is made by polymerizing chloroethene, otherwise called vinyl chloride. The equation is usually written as shown. Polychloroethene is used to make a wide range of things, including guttering, plastic windows, electrical cable insulation, water pipes, sheet materials for flooring, footwear, clothing, etc. Polyamides are polymers where the repeating units are held together by amide links. An amide group has the formula CONH2. An amide link has displayed formula shown. Polyamides are formed from monomers which are diacids and diamines, or monomers which possess both the amine group and the carboxylic group, for example, amino acids. Nylon 6,6 is so called because it is synthesized from two monomers, each of which has 6 carbon atoms per molecule. One of the monomers is hexane dioic acid with a COOH group at each end. The other monomer is 1,6-diaminohexane, also known as hexane 1,6-diamine with a NH2 at each end. When these two compounds polymerize, the amine group loses a hydrogen atom and the carboxylic group loses a hydroxyl group. This results in the carbon from the carboxylic group bonding to the nitrogen of the amine group to form the amide bond. The hydrogen atom and the hydroxyl group combine to form water. 1 molecule of water is lost each time 2 monomers combine. This is condensation polymerization. This process continues until a nylon 6,6 chain is built up as shown. Nylon is used in textiles for clothing and carpets. A lot of nylon is used to make pneumatic tire cords. The fibers are also used in ropes, and nylon can be cast into solid shapes for cogs and bearings in machines. Proteins are made up of chains of amino acids called polypeptides. Polypeptides are polyamides formed by condensation polymerizations between amino acids. An amino acid has the general formula H2N-RCOOH, where R varies both in type and number to give different amino acids. A condensation reaction takes place between the carboxylic acid group of one amino acid and the amine group of a neighboring amino acid to form the amide bond with the elimination of water. The amide bond is often referred to as the peptide link in reference to polypeptides. A polypeptide chain can consist of 100 to 300 amino acid residues. Polyester is a polymer where the individual structural units are held together by ester linkages. An ester link has the displayed formula as shown. A polyester is made by a reaction involving an acid with 2 COOH group, a dicarboxylic acid, and an alcohol with 2 OH groups, a diol. Polyethylene terephthalate, or simply polyester, is synthesized by condensation polymerization from two monomers, namely benzene 1,4-dicarboxylic acid, terephthalic acid, and ethane 1,2-diol, also known as ethylene glycol. When these compounds react, the hydroxyl group gives up a hydrogen atom, and the carboxylic acid gives up a hydroxyl group. The oxygen of the hydroxyl group then bonds with the carbon of the carboxylic group, resulting in the ester link and the corresponding loss of water formed by the combination of the hydrogen and hydroxyl group. Depending upon the processing, a variety of products are possible. If cross-linked, it is made into clear plastic soft drink bottles. It can also be made into textile fibers known as dacron or terylene and accounts for 50% of all fibers used to make clothing. Blended with cotton, dacron is made into no-iron clothes. This same polymer, with the trade name of mylar, when made as tape, is magnetically coated for use in tape recorders and videotape machines. Polysaccharides are polymers made up of many monosaccharides joined together by glycosidic bonds and are therefore very large, often branched macromolecules. Examples include storage polysaccharides such as starch and glycogen, and structural polysaccharides such as cellulose and chitin. Considering that the repeating units in the polymer backbone are often 6-carbon monosaccharides, C6H12O6, the general formula for polysaccharide can be represented as C6H10O5N, where N varies from 40 to 300,000. Starch is a naturally occurring polysaccharide consisting of a large number of glucose monosaccharide units joined together by glycosidic bonds. Glucose can be considered a polyhydride alcohol where one terminal hydroxyl group loses a hydrogen atom and the other terminal hydroxyl group is lost altogether. Hence, the two carbon atoms are joined via an oxygen atom with the elimination of water formed from the lost hydrogen and hydroxyl group. Starch is built up as follows. A molecule of starch can have hundreds of thousands of glucose residues. The process is summarized by the following equation. NC6H12O6 bracket C6H10O5 bracket N plus NH2O, where N can be of the order of hundreds of thousands. Starch is a storage carbohydrate in plants. Starch in its basic refined form is used in cooking to thicken foods such as sauces and as laundry starch. In industry, it is used in the manufacturing of adhesives, paper textiles, and body powder. It is used as a mold in the manufacture of sweets such as gums and jelly beans. Monomers chemically combine to form polymers, and like all chemical reactions, the product is a unique chemical substance with its own set of chemical and physical properties that are different from the chemical and physical properties of the reactants. To illustrate this point, the chemical and physical properties of glucose and its polymer starch will be compared. Glucose is a white crystalline solid at room temperature and pressure, while starch is an off-white powder at room temperature and pressure. Glucose is sweet to taste, while starch is not sweet. Glucose is readily soluble in water. Starch is insoluble in cold water and sparingly soluble in hot water. The melting point of glucose is 146 degrees Celsius, but starch decomposes at 250 degrees Celsius. Glucose is a reducing agent, as evidenced by turning Benedict's solution red and decolorizing acidified potassium permanganate solution, while starch has no reducing properties. Starch forms a blue starch iodine complex with iodine, while glucose does not effect any change.